Welcome to AXISVM. In this video, we will cover the design of the Slab model described in the step-by-step tutorial on the AXISVM website. In AXISVM, create a new model by clicking on the New icon. Set the model file name to Slab, select Eurocode from the design codes, and set the units and formats to EU. The slab will be designed according to Eurocode 2. After closing the window, select the Elements tab and click on the Draw Objects Directly icon. Change the element type to Slab, and in the next window, click OK to browse cross-section libraries. In the list of materials, select C25/30, then click OK. Now change the object type to Plate, and then set the thickness of the plate to 200 millimeters. Then click on the Complex Slab icon. The geometry of the slab will be defined by entering coordinates. Define the first coordinate by setting x equals 0, y equals 0, and z equals 0. Then press Enter. Define the next point by setting x equals 7.9, y equals 0, z equals 0, then press Enter. Now click on the Arc by 3 Points icon in the window and define the contour points by typing x equals 0.5, y equals 3.4, z equals 0, then press Enter, and again x equals 0, y equals 6.8, z equals 0, and then type Enter again. Now click on the line icon and type x equals minus 7.9, y equals 0, z equals 0, and then Enter. Type Enter again to finish the contour drawing. Then exit from drawing the object by pressing Escape. Now, move the origin of the local coordinate system to the bottom left corner of the slab by moving the cursor to that point and pressing the Insert key. Then, on the Geometry tab, click on the Node icon to create additional inner points. Enter the coordinates x equals 6.4, y equals 2.2, then type Enter. And then enter the point x equals 0, y equals 2.4, and type Enter again. The coordinates are relative. After the first node is created, the relative origin jumps to the specified point. Press Escape to close the function. Note that the thin red line represents the contour and the type of the domain. Moving the cursor over the contour displays properties of the element. Now change to the Elements tab. To define nodal supports, click on the Nodal Support icon, then select the inner nodes. Confirm with OK. In the next window, click on the Calculation button. Here, the stiffnesses of the support can be automatically calculated if the main parameters are specified for the columns. Click on the New Cross-Section icon and then on the Rectangular Shape icon. Set both B and H in the window to 300 millimeters. Click Place and then click anywhere in the window to place the cross-section. Then click OK to both name and save the cross-section. Then set L equal to 3 meters. And then click OK. In the Nodal Support window, the stiffness components will be set automatically with the calculated values. Click OK to close. To define line supports, click on the Line Supports icon. Then select each of the straight edges of the model. Confirm selection with OK, and in the window, click on Calculation to automatically calculate the stiffnesses considering the support conditions. In the next window, set L equal to 3 meters and D equal to 300 millimeters. Then pin both end releases by clicking each icon. Confirm settings with OK, and the calculated values will be displayed in the Line Supports window. Click on OK to close it. Now change to the perspective view. The next step is to define the load on the slab. Click on the Loads tab, then click on the Load Cases and Load Groups icon to add new load cases. In the next window, click on the automatic load case and rename it to Self-Weight. Close the window with OK, and the previously edited load case will be active. Click on the Self-Weight icon and select all elements. By clicking OK, a red dashed line will appear parallel to the contour line indicating the self-weight of the domain. Again, open the Load Cases and Load Groups window and create a new static load case with the name Finishes. This load case will contain loads from the slab finishes. Close with OK. Click on the Distributed Load on Domain icon, and in the window, set PZ equal to -2.5. Assign the load to the slab by clicking on the Distributed Domain Load icon, then click inside the domain. Now close the window. To define the line load on the arched perimeter, click on the Domain Line Load icon. In the next window, set PZ1 and PZ2 both equal to -1. Select the Arc by 3 points icon from the bottom row, and then click on the bottom, central, and top points of the curved edge. Click again on the top point of the edge, and then press Escape to exit. Now switch on load intensity using the numbering function in the bottom right corner at the speed buttons. Click on numbering and then check the load value and units checkboxes. Now create a new load case with the name Live. Specify the live load on the slab in this load case. Set the load intensity to -3 in the Z direction and define the distributed load on domain as done previously. Now, load combinations should be set. Activate the Load Combinations icon to open a window. Here, create the first load combination by clicking the New Row icon. Set the self-weight and finishes factors to 1 and the live factor to 0.3. Then select the SLS quasi-permanent load combination type. Now create a second load combination. Set the self-weight and finishes factors to 1.35 and set the live factor to 1.5. Then set the ULS ultimate limit state combination type. Click OK to confirm the load combinations. We have now finished with the basic data input, but a mesh must be generated before any calculation is done on the model. Select the Mesh tab. Click on the Domain Meshing icon, then select all of the elements. Confirm with OK. In the next window, select Quadrilateral as the mesh type and set the average mesh element size to 0.65 meters. check the Fit Mesh to Load checkboxes and activate the Adjust Mesh to Column Heads function. Click OK to start the automatic mesh generation. After the mesh finishes, activate Display Options and on the Symbols tab, check the Surface checkbox. Close with OK and the local system will be shown on every finite element. The red line denotes the X direction, yellow denotes the Y direction, and green the Z direction. After viewing this, switch off the surface elements. Then click on the Static tab to analyze the model. Click on Linear Static Analysis to run the analysis. The program checks the model, warns to set nodal degrees of freedom, and offers to set them automatically. Check the Save Model with these settings checkbox, and the degree of freedom settings will be saved. Then click Yes to accept the suggestion, and the program will continue the analysis. When the calculation is finished, close the window with OK. The program automatically displays the vertical deformations considering the self-weight load case in the Isosurfaces 2D display mode. Select the load combination CO number 1 to check the serviceability limit states. Deformation values are negative because the positive direction of the global z-axis is opposite to the specified load directions. To find the location of maximum deformation, use the min-max values function. Select one of the deformation components and confirm with OK. The program shows the maximum negative value and its location. Click OK to continue, and the results show the maximum positive value. Now select the Isolines display mode. From the drop-down menu, select Surface Internal Forces MX. The MX moments will be displayed. The MX specific moment represents the moment that rotates around the local y-axis. Then select Load Combination CO number 2 in order to check the internal forces of the slab. The result components can be observed in different display modes. We can also check the results for the MY moments. Now change in the drop-down menu to Line Support Internal Forces RZ. Activate Result Display Parameters and check Write Values to Lines to see the result values. More details and further analysis of the slab model can be found on the AXISVM website, along with additional tutorials and guides. Thank you for watching.